Have you ever just watched a storm rolling in over the ocean and thought, how on earth can we even begin to understand that kind of raw, chaotic power? Well, today, we're going to pull back the curtain. We're going to see how scientists and engineers use nothing but math and lines of code to build their very own digital storm right from scratch.
So that's really the big question for this whole explainer, right? How do you take the wild, untamed energy of nature and bottle it up into a simulation you can actually study? You'd think it's impossible, but the answer, and this is the cool part, lies in breaking down all that complexity into some surprisingly simple rules.
Okay, let's dive right in. Our whole journey starts by looking at the two things that make an ocean storm a storm. You've got the wind that drives it, and you have the waves that rise up to meet it. We're going to build both of them piece by piece.
First things first, the wind. I mean, how do you even begin to program something as unpredictable as a gust of wind? It's not like you can just plug in one number. You have to capture that constant, random, fluctuating feeling. So, how do they do it?
Well, the model starts at this beautifully simple idea. The wind at any given moment is just two things added together. A steady, average wind speed, that's the mean, plus this chaotic, fluctuating part, the gusts. And the secret is that these gusts are designed to average out to zero over time, but they're where all the chaotic energy comes from.
Okay, so how much gusting are we talking about? To control that, the model has a dial, basically, called turbulence intensity. And here it's set to 15%. What that means is the typical gust is going to be about 15% of the average wind speed. So, for a 10 meter per second wind, you're looking at realistic fluctuations of about 1.5 meters per second. Totally believable.
But here's the catch. You can't just use pure randomness. If you do that, you get what's called white noise. And it's like TV static. It's too jagged, it changes way too fast. It's not like real wind at all. Real wind gusts are slower, they have more flow to them. So to get that, we have to filter the white noise, smoothing it all out into what's called colored noise. And that has the slower, more natural feel we're looking for. So let's put that all together. The recipe for virtual wind is really just 4 simple steps. Step 1, you start with that raw, staticky randomness. 2, you smooth it out with a filter. 3, you scale it, you dial it into that 15% intensity we talked about. And finally, 4, you add it on top of your average wind speed, and boom, just like that, you've got a realistic gusting wind signal all ready to go. All right, so we've got our virtual wind. Awesome. Now we need to create the ocean surface for it to blow on. Now this seems even more complicated, right? But the idea behind it is just as elegant. Here is the absolute secret to the whole thing. Don't think of a chaotic ocean as one big, messy wave. Instead, picture it as a chorus of thousands of tiny, simple, perfectly smooth little waves all singing at once. Each one is just a perfect little cosine wave, but when you add them all together, you get that incredible, irregular, unpredictable surface of a real sea. So if the waves are a chorus, they need sheet music, right? Well, that is exactly what a wave spectrum is. It's the mathematical sheet music that tells our simulation how much energy or how much amplitude to give to each and every one of those simple little waves. A spectrum for a calm day will put energy into long, slow swells. But a storm spectrum, like the one we're using, it packs all its energy into powerful, choppy, high-frequency waves. And the process for building the wave is another simple recipe. First, we pick our sheet music. In this case, it's a famous model called the John Swap spectrum. It's basically the perfect score for a storm-driven sea. Then, for every little component wave, we use that spectrum to find out how big it should be. Then, we give each one a random starting point, or phase, so they're all out of sync and don't just line up. And finally, we just add them all together. The result? A digital ocean. Now, creating a simulation that looks right is one thing. That's cool. But creating one that is scientifically accurate, that's a whole other ballgame. And this is where we have to be really critical and ask ourselves, is what we built just a good approximation, or is it the real deal? The original analysis of this particular code points out something super important. That wave spectrum we used, it's not actually the official textbook John Swap formula. It's a simplified/heuristic version, which is a fancy way of saying it's a practical shortcut, a clever trick designed to get a result that looks good, even if it's not perfectly physically accurate. So what's the actual difference? Well, the simplified model takes the formula and multiplies it by a shaping factor. The official, or what scientists call the canonical model, actually sticks that factor inside an exponent. Now I know, it sounds like a tiny, nerdy mathematical detail, but if you're a scientist trying to precisely match real-world data, that subtlety is everything.
It's a great reminder that in the world of simulation, the details matter a lot.
So after all this math, all this code, you might be asking yourself, okay, but why? Why go to all this trouble? Why do we need to build digital storms with this level of precision? Let's zoom out for a second and look at the real-world impact.
To really get why this is so important, let's talk about a super powerful technique called normalization. Instead of looking at the raw power of a storm, meters per second, all that, we can scale all the data to fit on the exact same chart, from -1 to 1. What this does is it lets us ignore how big the storm is and instead compare the fundamental character or the shape of different storms. Are the gusts sharp and fast? Are the waves long and rolling? Normalization lets us compare their personalities.
And this is why it is all so absolutely vital. We build these digital oceans to test the designs for ships and oil rigs before a single piece of steel ever touches water. We use them to see if a giant offshore wind turbine can actually survive a 100-year storm. These models help us predict floods, understand climate change, and yeah, they're also how you get those jaw-dropping special effects in movies. This isn't just some academic exercise. This stuff has huge, profound, real-world applications.
And all of this leaves us with one last big thought. We've just seen how one of nature's most complex, most chaotic forces, a raging ocean storm, can be taken apart and rebuilt from a set of simple, almost elegant rules. And it just makes you wonder, doesn't it? If we can code a storm, what other parts of our complex world can we understand by doing the exact same thing? What other chaotic systems are just out there, waiting for us to find their simple, programmable rules?